WebRTC, or Web Real-Time Communication, is a free open source project that provides web browsers, mobile applications with real-time communication. We're going to define what that means via a simple application programming interface, API. That's the goal. The goal is, let's define a protocol that connects peer to a peer. That's the shortest possible, lowest latency path. And let's provide a nice API that is simple for everyone to use. And once you put it in the browser, it becomes a standard. And once it's a standard, the friction goes away. It's a great technology. How about we jump into it? Guys, you have no idea how long I've been researching this tech. Now maybe it's 2 years now. It's on and off, and you guys gave me a lot of resources and asked me a lot of great questions, and this was one of the most requested video to make on my channel. So here it is. I don't know how long it's gonna take, but there's a lot of work, there's a lot of content. There's some demos that we're gonna do, but here's my plan for this video. We're gonna discuss WebRTC as an overview. That means we're gonna remove the details first. This is for people who are interested about the idea, not the details. So we're gonna talk about that, just overview how it actually works, and then we're gonna dive into the meat and potato of WebRTC, and we're gonna demystify every single thing out there. WebRTC, in order to explain that, you gotta understand NAT, and I thought I understand NAT, and apparently I did not. So I dove deep into NAT, learned a lot about NAT types and method and translation method, and we're going to talk about that. We're going to talk about what is stun, what is turn, what is ICE, what is SDPU signaling, this DB. All of this stuff exists for a reason. So always ask the why, and then find out how to use it, only if you know what exists. Once you know, it's powerful. Then we'll go through a demo, guys. I'm going to do a demo. And for the demo, guys, I'm not going to do the media chat that every single one in the tutorial does. I'm going to do a simple chat between two parties. And guess what? I'm not even opening Visual Studio Code or anything like that. We're going to literally open two browsers and let them communicate with each other. How? We're going to write code in the dev tools, because that's the best thing. Every single line of code I'm going to write from scratch, and every single line of code we're going to explain it, because that's what we do here. No copy and paste, no magic socket IO that does everything for us. No, we don't do magic here. We understands everything. So we're going to talk then about the pros and cons about WebRTC, guys. What's bad, what's good about this technology, right? Because nothing is perfect, obviously, and whether it's for you or not. And then I added in another section to talk about anything WebRTC and beyond, because there's so much that I can't possibly cover. So I'm going to point you to a lot of resources, and you're going to find in this YouTube video description, you're going to find tons of resources that I've researched and collected from you guys, from my own research. So feel free to touch upon all these resources to learn more about them. How about we jump into it? So WebRTC overview. So the first question is, why did we build this thing? We built it because we needed to transmit media, that is audio and video, in a standardized way, in a low latency way. When I say standardized, I mean I need an API that is simple to use. And when I say low latency, I mean I need a proper protocol. So UDP is always a good choice, right? Because there's no much acknowledgements going on there. But still, we need a little bit better protocol. So we need a peer-to-peer connection, because if I rely on another server to relay my content, that adds the latency, because there's whether it's a reverse proxy or it's a turn hop, you have to terminate the traffic, look at the traffic, process the traffic, and then re-encrypt, decrypt the traffic, and then go by your own merry way and transmit to the other side. So this is all adds cost. And for the video, that you don't want to do that, because especially when you're live streaming or doing something like that, you want to chat, you want things to come as fast as possible. So peer-to-peer is the fastest path. That's what we want here. So how do we talk peer-to-peer, right? Is this torrent kind of thing? Yeah, kinda. We'll talk about that. And it also enables rich communication between browsers. Browsers, for the longest time, we didn't have rich stuff. Now we have all this beautiful video, and we have access to the camera, we have access to the mic. Let me use it, right? Without writing my own app from scratch. Just fire up the browser and has all the APIs I need and just use it. So in an IoT mobile browser devices, they all just communicate once you have this WebRTC. We're gonna demystify this stuff in a minute. So let's go through a scenario. What exactly happens in WebRTC? This is what happens. A want to connect to B, right? And they don't know each other. This is the funny part. A does not know that it wanted to connect to B, because how does it know, right? They just want to know this information. So A needs first to find all possible ways that the public can connect to it. Not B, but the public. Who can connect to me? Hey, do I have a public IP address that people can just hit and use? Well, maybe yeah, maybe not, right? If not, then do I have any access? Like, is my router allowing me to expose my port forwarding rules? Do I have a public presence on the router? All this stuff, we're going to talk about it in details. B does the exact same thing. And what they also do some more stuff. They ask, hey, this is the encryption I support. This is the security parameters I support. This is the video compression I support. So, and it start collecting information. Remember, it didn't send it to the other party yet. It just collects a lot of information, and it creates this what we call an offer. So then A and B start signaling this session information that they collected, right? Their encryption keys, their security parameters, their audio, their video information, their communication, public IP addresses, anything. And then somehow this file, this information becomes like a huge bunch of hunk of string, and this needs to be transmitted to B somehow. How? WebRTC comes and says, we don't care, just transmit it to the another communication. You might say, come back, Hussein, wait a second, I came to WebRTC to communicate from A to B. If I have already a way to communicate from A to B, I wouldn't need WebRTC. So that's the silly part in WebRTC. It's like, well, it might sound silly if you think about it. Well, yeah, we'll let you connect A to B as long as you're already connected, because we need you to send some stuff. I was like, what? That's kind of silly. But if you think about it, whatever communication you're going to have is not going to be as fast and as optimal as WebRTC. So throw this a bunch of string that you collected, this information, this session information that's called SDP, the Session Description Protocol, and send it over to B somehow. Tweet it at him or her, do a QR code and scan it, send it via WhatsApp or WebSockets. That's the popular thing, by the way. HTTP fetch or XHR, send it somehow. It's just string. It's just a bunch of a string collected, and then once you send it, B does the same thing and send their information back to you, and then we will know how to communicate with each other behind the scenes without this signaling protocol. That's what it's called, signaling, right? Without WhatsApp, without QR, without tweet, without WebSocket, without any of this stuff. So now finally A connects to B via the most optimal path, and that's how things work. So let's go to an example. So A want to connect to B. This is so A asks question, how can people reach me? Hey, you can reach me from A1, A2, A3. You might say, what is this, right? These are public interfaces. Like, hey, this might be the public IP address of A. This might be a NAT traversed public IP address. This is another method of communication via, I don't know, another third party. So it finds all possible communication. It also finds security parameters, media information, and then B does exactly the same thing. And then somehow they communicated to each other. This is how they communicated. How? It's not through this internet network. No, it's some offline concept, right? WhatsApp. And then once A finds the B's information, says, oh, looks like B2 is the available optimal path. Let's use it. And A1 will say, oh, and B will say, hey, A1 looks like the optimal path. They will essentially connect directly. That's the shortest possible path, right? And this is the internet, so there are lots of hops in the middle, but who cares? So that's essentially how WebRTC works, guys. How about we demystify it with actual word instead of doing all that stuff, right? The overview. In order to demystify WebRTC, we really need to understand NAT, and we're going to understand it deeply. So we're going to dive deep into details of NAT here, right? Network address translation. And then we're going to explain why do we need stun, right? And then why do we need turn, and what is that really? Then we're going to explain ICE. Then we're going to explain the SDP, the session description protocol, that thing that we send via WhatsApp, as we said. And then we're going to describe the signaling, which is the WhatsApp or the WebSocket or the QR or the tweet, right? And the signaling of SDP, right? All of this will be explained again, and then we're going to jump into a demo soon. So network address translation. Guys, if you have a public IP address exposed, you don't have any problem, because you will listen on a port, right? Like a web server, and then you will give this port to someone and the public IP address, and someone will connect to you directly. That's how, if you spin up an AWS EC2 instance, that's exactly what you get. You get a public IP address. So that's pretty cool, right? So that's the idea. But if you are behind NAT, which is almost everybody is, right? If you have a router and your Mac or Windows is connected to the Wi-Fi or LAN, you're behind NAT. So you don't have a public IP address. Your router does, right? And your router has a public IP address, let's say 5555, and your router also has a private IP address, and it's called the gateway. And this is you, and other device will be 2, 3, 4, 5, 6, 7, okay? So that's the private IP address. And we talked about NAT, guys, many times on this channel. Check out the video right here. But this is what you want to go to. You want to go to 444.480. You want to, I know, this is a web server. This is Google. This is somewhere, right? How do you visit that? Right? What you're gonna do is you gonna construct the packet, say, hey, I want to make a GET request to 444.80, and this is my source IP address 10.0.0.2.8.9.9.2. The first thing your machine does is says, okay, can I actually communicate with 444.480? Right? It does something called subnet masking. It says, okay, is this in the same subnet mask? So it's going to do 255.255.255.0, and it's gonna do an XOR, I think an AND, not an XOR, and then we'll say, oh, this is definitely not in my subnet, right? Because it's going to end up with 444, and yours is 10.0.0, right? So it's not in the same network. So I cannot communicate directly to this IP. So if the machine cannot directly communicate to that, if it's not like, I don't know, 10.0.0.3, for example, it will say, hey, gateway, help, help, help. You should know how to communicate to this. I don't. So you will send this to the gateway, which is 10.0.0.1. And you might say, Hussein, do I replace the IP address to be 10.0.0.1? No, if you do, you're going to lose the fact where you're going. So what you do is you add an ARP request and you add the MAC address of the router. So we talked about all of that in the NAT video. And then somehow your machine delivers this to the router. And the router says, okay, this machine is, this device, this packet is not really intended for me, right? Because this is the destination is not 10.0.0.1, but it was sent to me through the layer 2 framing, right? Because the destination MAC is me as a router. That means that this guy or gal want to go to outside world. But guess what? I'm not gonna let you go outside the world like this naked, because nobody will understand 10.0.0.2. You're gonna get slaughtered out there. It's a very dangerous world out there. Take this, right? So what the router will do, okay, let me talk on behalf of you, because I understand the wild west, and I have a public IP address to talk to. the rest of the people out there. So it does. It replaces that. It replaces the fact that it's HG10002 with another different port, right? And we talked about that random ports just randomly so we can know how to send the information back. But before it does that, it creates a beautiful table, and this is called the NAT table. It says, okay, internal IP 10002 with internal port 8992 wanted to communicate to 444 on port 80, and I have as a router assigned an external IP address 5555-3333. And that, let me remember that, so if I got information back, I know how to swizzle and change the IP address to send it back. So let's continue. I send that information back, and the server gets the get request. We process the information, we get request, and I know query the database, get an index to the HTML page, whatever. And the server now is about to respond. What does it respond to? Does it respond to this? No, because it doesn't know. It responds back to the router 555333. That's what it was received, right? Okay, 200. Okay, let's do this. We're gonna send it back. It sends it back to the router. The router looks at it, says, okay, who is 555333? The destination, because it's not for him or her, the router, right? So the router says, okay, let me look at the table. 5553. Oh, that's this. Let me swizzle that back, right, to 10.0.0.8.9.9.2, and then now I know which server to send it to. I send it back. So that's how NAT works, right? I had to explain it. I know it's going to be a long video, guys, but this is very critical to understand, because once you understand this, you can understand WebRTC, because there is so much to NAT other than this. Okay, and that's it. So let's discuss the NAT translations method, or translation methods maybe. So there are 4 types, and again, guys, the router, I don't know why I sounded British. The router have 4 methods, but every router have a different implementation, to be honest. Not every router will implement this the same way. It's just different implementation. So take that with a grain of salt. But this is the main implementation method, translation method. There's one-to-one NAT, what's called full cone NAT, address restricted NAT, port restricted NAT, and symmetric NAT. We're going to talk about them now one by one. All right, but just know that WebRTC by default works beautifully with these 3. It does not like this one, right? That's why we need another mechanism. Once you have symmetric NAT, you're basically useless to me. I rather communicate with WebSocket. That's my opinion, personal opinion. Once you have this, when you fit into this scenario, just throw WebRTC. In my opinion, just throw it. I don't see a value for it, unless maybe the beautiful API and stuff like that. But we'll discuss. But again, 90% of the communication is actually done with these 3. Let's communicate. Let's explain these things. So one-to-one NAT or full cone NAT. Full cone NAT. Packets to external IP port on the router always map to the internal port IP without an exception. So let's say you have a public presence of 555333, right? Which you created, which we pinched hold when we visited 444.80.80, right? If someone sent you a packet to the router, if it's configured as a one-to-one NAT, it will always send the packet to you. It does not check where is it coming from, whether it's coming from 444 or 666 or any other IP address or any other port. It does not care. It will automatically forward that. So that's called full cone NAT. Okay, let's take an example. Here's a NAT table with pre-configured IPs. Right, this is the current state of the NAT table. This is you, this is the router, and there are 4 packets that are incoming. I want to let you know that we're going to go through each packet and see which one will pass, which one will fail. So this packet is directed to 555333. This one is also the same thing. This one, so all of them are directed to the router on port 3333. And the IP address is the public IP address of the router. So technically what we want is we want to go to 10.0.0.2 8992. This is the packets want to be delivered to this. But let's see, when one-to-one NAT or full con NAT, can we do it? Well, let's see. This is going to this. We don't care. We don't check where is it coming from. This one is coming from this IP address and this port. Let it through. This one is coming through. This is let it through because I can find it. It's right there, right? Let it through. Once it's there in my NAT, I'm gonna allow it. Let it through. Let it through. I don't care. That's one-to-one NAT. Beautiful, because once you have one-to-one NAT, if your router is configured this way, and I truly don't know how to find out if your router is configured to be this without actually testing it, right? That's one-to-one NAT. So that's the best thing we can do. That means once I visited something, right, and I got this IP address, if I got this information, if I got the fact that I am 5555 on port 3333, I can send it to someone else, and they can send me a stream of content, of packets, without them having to establish pre-communication with them. Right? That's great, right? That's great for WebRTC. That's great for peer-to-peer. Let's continue. Address restricted NAT, because some routers will restrict. It says, you know what, this is a little bit dangerous. We want at least to restrict some of this stuff. Yeah, if you gonna visit this port, this IP address, we want to let you know at least, did we actually communicate with you before? Are you good? Are you not shady? That's what we want. So we check the address. That's what it's called, address restricted NAT. So packets of the external IP port on the router always map to the internal as long as the source address from the packet matches the table, regardless of the port. If we found that we visited you before, whether in this entry or other entries in the NAT, we're gonna let you in, son, because that means we trusted you before. We communicated, so the firewall actually allowed you in, so you're kind of good. We'll allow it. So allow if we communicated with this host before. That's what it means. Right? Example. So according to this new pieces of information, what would pass and what would succeed and what would fail? So let's see. Now we need to look at this, right? Now we have to. We cannot not look at this. So we're going to this, and this is coming 4444. Did we visit 444 before? Yeah, it's right there, right? So this packet will pass. Let's look at this. This is going to 555333, right? But it is address this, right? Well, we didn't visit this address for that particular pair, but we did visit it on another pair with another communication. So let it in because we trusted this IP address. How about this? Well, 333, we just visited it, right? Let it in. 9812, nope, it's not on my, nope, we have not communicated with this before. I'm sorry. If I did not communicate with you, I do not trust you, right? So we allow communication from addresses that we actually communicated with before. Doesn't matter how. Maybe we sent a UDP packet, maybe we sent a DNS request, maybe we sent a telnet request. As long as you sent some packet and it is in your NAT table, you're good. Let's go through port restricted NAT. So it's exactly the same thing, but you have to match both address and port. Let's go through an example, I guess, right? It's easier this way. So port restricted NAT is port and address restricted NAT. So let's look at this. Did this puppy visit me 444 and port 80? Well, it's right there, so it's gonna let it pass. Did 3333 port 22 visited me? Oh, no, they did not, right? Because this is 333 port 80. This is 333 port 22. So, nah, nope. So this packet comes from 333 8080. Oh yeah, we did visit it 38080 right there. So we'll allow it in. This guy is not. This address is not even there in my table. So nah. So that's port restricted NAT. Symmetric NAT is the most restricted one, and to me it's the one that makes more sense security wise, that is, right? So you can send me packets if exactly you matched the same full pair. I'm not looking at the whole table. I'm looking at the thing that you want to request. You want to go to 55553333, you better be the actual destination and port. If you're not, I'm not gonna let you in. That's exactly it. So it has to be the exact same 4 pairs, which is very, very, very restricted. It's a symmetric, right? That's why there's a symmetry, right? We're not looking at something else, right? Let's take an example. So for this guy, that's the only pair that matches. Hey, I want to go to 5555 on port 3333, right? Okay, who are you? You better be 4444 on port 80. Oh, well, you are? Let you in. But let's take another example. I'm going to 444, but I am 3333 and port 22. Well, are you 444? Nope, you're not. But wait, I am actually an address that I visited. No, I don't care. You better be the same exact match that we visited you before. That for that particular entry. Nope. How about this 33380? Nope. But I'm right there. No, I don't care. You better be right here, star. So bang. And obviously this address doesn't even exist. So bang. So that's how symmetric NAT works. And this does not work with WebRTC. We're gonna find out why, because WebRTC uses something called a stun server. Was gonna know, and then literally communicate with the stun server and gives you the IP address. And guess what? Once it does that, it opens a public presence. But guess what? If it's symmetric NAT, that means only the stun server can communicate back to you. You cannot send that public information and send it to some shady peer-to-peer Alice all over the globe to communicate to you, because that pair was created for the stun server. So that's why it doesn't work. So let's go ahead and complete stun. Speaking of stun, session traversal utilities for network address translation. Session traversal utilities for NAT. Stun. Just weird naming, to be honest, right? So we traverse the session. It's a bunch of utilities, right? One of the utilities is just, hey, tell me my public IP address and port through NAT. That's it. That's the job of stun. So you can see how cheap this thing to run, right? Because, hey, I'm going to communicate to you, take my source and port IP ports and the layer 4 information and put it in a packet and then send it back to me as data. That's what it does, right? So it works with full COM, it works with port address restricted NAT. It does not work with symmetric NAT, as we explained. Why? Because the moment I ask you to give me my public information, that pair was created just for you if it's symmetric NAT. So I cannot use it somewhere else. It's symmetric. So it's going to be symmetric with you and me. That's it. It's you and me, Papa. That's it. You don't involve the pote. Stun server usually runs on port 3478, but doesn't have to. You can spin it on any other port, just like any other application. And for TLS, for secured stun, you can do 5349. And it's cheap to maintain because you can literally spin up a Docker container that has a stun server, and it's very, very lightweight because it doesn't do anything. It just literally responds back with the content. Right? There is a format, obviously, but that's why Google gives you public stun servers, because they don't care. They're so cheap to maintain. Let's go through a stun request. And did we talk about why we need a stun, right? This stun server, we need it so we can find out our public presence, so we can communicate this public presence to someone else so they can communicate with us. That's the goal of stun, because we're behind NAT. If we have a public IP address like we did in the 1996 and 1998 and 1980 and the early 2000, we wouldn't have a problem. But unfortunately, we do have to use this. So here's what do we do? We create a packet. It says, okay, I want to request my stun. This is just normal random package, right? This is the destination 9999347. I want to go to this stun server, and this is my IP address. This is my random port. Send it to the router. Router does natting. Change that. Hey, I can't let you go naked, right? Let me put some cloth on. Put my public IP address. Poof. Send it over. I obviously create the NAT, that's like normally, just like anything else, right? And then they send it to a server, and the server say, yeah, what is this exactly? You want to stun? Sure. I'm gonna take your public presence, right? Now you are 55553333. Push it into a packet, literally just response into a packet, and send it back to the server, to the router. Now the router will change that information. It will change 55533, right? Remember? because it looks in the NAT and change it, we just lost the information that we are 555333. But we did not really, because we send it as a packet. And it's also encrypted if you're through the encryption TLS, right? So technically, now I know this packet information. I'll send it to the user. I all of a sudden know my public presence. That's what a stun does. Very, very lightweight, very simple. This is what stun when it works. Let's take an example. So I am an IP address 192.168.1.2 behind a router. Obviously, I just didn't draw it because I don't have space. And this is another computer on another router on another ward, right? 10.0.0.2, also behind a full cone NAT, which is a 1-to-1 NAT, right? Which is the best thing. So this asks me, hey, who I am? You are 555333. That's exactly what we showed, that in details, right? B, this machine also does the same question. Who am I? Hey, you're 777 on port 4444. And now both of them have information, and they exchanged it somehow with the signaling that we're going to talk about. Now, this one took to this. It says, hey, 7773, I am 553. Let's connect. If it's full connect, remember, those guys didn't connect before. But because it's full cone NAT, it's going to allow it in. It says, sure, I'm going to allow everybody in my home. It's full cone NAT. It's not even address restricted. If it's address restricted, we're going to explain a little bit. Let's finish this up. Right. So now I respond, oh, sure, let's connect. But let's say if I am behind an address restricted NAT, what are we going to do? Obviously, the moment you send that request, it's going to fail. Because it's like, who are you? I don't know you. Right? So what you need to do is you need to at least establish a communication prior with this server, right? So you want to communicate to the server somehow, you send a packet and you establish presence with this, right? So that this address is saved here, and both of them should communicate just at least randomly, right? Once you communicate, the address of this will be saved in the routers, right? And the address of this will be set in this router. So they will have matching addresses. So their addresses will match. And now I can actually send information. But before that, I cannot communicate, right? So this machine should attempt to connect first. And then this machine should attempt to connect first. And then once they establish, they will be allowed, right? And the same thing with the port, right? So and then that's it. And this is the shortest path with the lowest latency. That's the beautiful thing. Here's a stun when it doesn't work. So let's say this guy is behind a symmetric NAT, right? So you're gonna ask who I am, you're this. You're gonna ask who I am, you're this. But this guy want to communicate to this person, but the moment says, okay, 5533, yeah, you want to go with this, but I gave this IP address. Oh, this is actually a wrong thing. Let me fix it. All right, we just fixed it. So, hey, I want to connect to 77444. It says like, what? Who are you? I created this entry. It's my NAT, but it was for this particular server, not you. I don't know you, sir. Nope, you cannot connect. So that's the idea of creating this kind of content, right? You need this application to communicate with each other in order to allow that. But this is a scenario that basically doesn't exist. You cannot do it. You cannot communicate peer-to-peer. Meet, turn, traversal, using, relay, around, NAT, around it. Let's go around it. So that's basically, we know how this works. Like we have done a lot of applications as backend engineers that does exactly that. It just takes a packet and forwards it only. That's what a reverse proxy does, right? Almost, right? This is a little bit lighter weight in my opinion, because it doesn't just looks at layer 4 information most of the time. It doesn't do deep packet inspection like layer 7 proxy. But if in case of symmetric NAT, we have to use turn, right? It's just a server that relays packets. It doesn't do anything else. Just, hey, I want to communicate with this. All right, let me do it. Let me just do it. So all the communication goes through that hub, essentially. It is expensive, kind of expensive to maintain and run if you think about it. It's not free, right? You cannot just have it, right? So that's why nobody actually essentially provide turn servers for free for you. You have to spin up your own, essentially, if you want to. We're gonna talk about that a little bit. Here's an example of turn. So I am 555333 behind a symmetric NAT. I'm also behind a symmetric NAT, and it says, hey, send hello to 7744, please. And this person, this turn server is gonna send that information to that. Why? Because they already established a trusted NAT safe communication between them, and they also this does the same thing. So you can respond back, I can respond back to you, and I respond back to you. Nobody's communicating directly. They all go through this turn server. Awesome. So now we have a bunch of turns, we have a bunch of stuns, right? There is so many options. How do I pick the appropriate option? Or just collect all these options? Meet ICE, Interactive Connectivity Establishment. This is nothing fancy, but it's a protocol that says, hey, back to the overview. What are the different ways people can connect to me? Hey, you can connect through this stun server. This is a public IP. You can have a multiple stun servers. I don't know, one of them didn't work. The other one will work, right? So you have multiple public IP addresses through your router, and you have this turn server. And by the way, you have multiple local IP addresses, because guess what? Maybe your WebRTC server or the client is on the same NAT. So why would I need to communicate publicly? It's just let them communicate directly to each other. So it also adds the local IP addresses. It orders like the reflexive addresses, that one we talked about, stun ones, relayed through turn ones, all of that stuff. It just have this public IP addresses. In the turn case, you're gonna have the public IP address of the turn server as a candidate for relaying. That's how you do it, essentially. So that's what ICE is. It just collects all information and shoves it into something that we call the SDP, which is the most important thing in WebRTC, in my opinion. And these are called ICE candidates. So the IP address, local IP address, reflexive address, all of these addresses are called ICE candidates, right? So if you heard this ICE candidate, that means this is the possibilities of things that you can communicate through me. You pick. What do you want? Because one might work, what doesn't work, one might actually work, right? And collecting ICE candidates, this trickling concept, takes time. We're gonna show in the example in the demo. It really takes time, so you guys have a wait. And I made a mistake of not waiting, and I got all kind of errors. All the collected addresses are sent to the remote peer via SDP. Go down. Go peer via SDP, session description protocol. This shows up again, this SDP thing. This is the most important thing. That's the file, that's the hunk of string that we're gonna shove all the ICE information, all the video, all the media, all the security information in this string. It's just a bunch of long ass string that we just send via WhatsApp to the other party, or send via tweet to other party, so they can know about us. Right. So that's ICE. ICE very, 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 very critical, and we're going to show in the code. SDP, session description protocol. Description, focus on the word description, because it's going to show up in the code a lot. All right, so it's a format that describes the ICE candidates. It describes the networking option, it describes the media option, it describes the security option, other stuff as well. So much stuff, stuff that I don't even understand, to be honest, right? There's so much junk in this stuff. You can add your own junk in the SDP if you want to. Like this is exactly what Discord did. Check out the Discord video that they used WebRTC and they customized the SDP. They said, wait a second, we're not going to use a stun. We're going to use our own turn beautiful, what do they call it? Voice servers, right? So they built their own SDP, customized, and they just used that, right? So you can do that. That's what Discord did. So it's not really a protocol, it's a format in my opinion. I don't know why it's called protocol, but no, who knows? Most important concept in WebRTC is this SDP. This is the file, that's the string. The goal is this: take the SDP generated by the user and send it somehow, quote unquote, somehow, to the other party. And once you send it to the other party, we're done. How do we send it? I don't care. And that's kind of a double-edged sword with WebRTC, and makes writing WebRTC a little bit complicated if you don't know what you're doing, if you don't understand. And that's why I don't like using kind of framework that does everything for you. Because if you just use a tool that does all the magic for you without you as an engineer, again, I'm not talking about users, I'm talking about you as an engineer. You are an engineer. Take pride of your work and understand everything that you're using. Do not use black boxes, guys. Do not. You have to understand how this works, because if it breaks, it's shameful that you don't understand how to fix it, right? Or what happened, right? You might disagree with me on this one, but if you use WebRTC, know how it works. Don't use Socket.io and just some tools that, hey, it does the magic and just everything is amazing. No, this is not. Yeah, don't do that. SDP example. This is how it looks like. This is just an example. It's basically attributed. So one character equal value, and there is a attribute. So a equal this. This is the ICE candidate that we talked about. So this is, I guess, this is this is my private IP address. So this is another private IP address, and so on, right? So this then gives you another option. So many options. Obviously, it uses a UDP by default. But yeah, so powerful stuff. Signaling. So what is signaling? The idea of signaling is, hey, I just have this beautiful string now, right? This is I just generated. I did all the ICE candidate. I did all the security option. Now I have this file. Send it to the other party. How? I don't care. A lot of people use WebSockets and Socket.io to transfer this information to the other party, because you just establish a communication, then send this. As you find more candidates, you send it, right? So you signal that. The idea is, wait for all the ICE candidates to finish, because it takes time. Obviously, looking for the network takes time. Once you're done, create that SDP and just do a QR code and then post it on Twitter, and someone will scan it and they will have the SDP. Send it via WhatsApp, send it via tweet. Who cares? WebSocket, HTTP, does not matter. Just send the dang string to the other party. That's the signaling, right? No more, no less. Right. I tried to go through this video through the steps of the important steps here. Once we understand everything, now we have signaling, right? So when someone said, oh, it's DP signaling, you know what it means, right? It's basically, let's send this information to other party, all right? Again, the funny part is, hey, I'm going to communicate with you, right, through WebRTC, but first, please communicate with the other party and send it this. I was like, what the heck are you talking about? I am using WebRTC so we can communicate. If I already have a communication, why do I need you? That's what confused me the most in WebRTC. But once I understood that, okay, WebRTC can give you a little bit more performance than nice API with a peer-to-peer connection, it's maybe worth it. So you're gonna establish an expensive WebSocket server that does the signaling, and then once you're done, you relay down to WebRTC. That starts to make sense. But guys, if you have questions, if you're questioning something because you don't understand it, that means you're on the right path, right? Don't let people bully you into thinking that, oh, your question is dumb, you should not ask these questions. Ask everything. You have to ask everything, because guess what? If you have a question, a lot of the time, someone else will have the same exact question. Question everything. Do not care about what people think. WebRTC demystified. So this is exactly what's happened. Exactly what happened in the code. Here's the thing. A wants to connect to B. A creates an offer. What's an offer? You say, you just mentioned this word. We didn't ever mention it. Don't worry. Offer is just exactly the SDP. It's just another name for it, right? So we create an offer. What does an offer do? It finds all the ICE candidate, which we talked, hey, you can connect to me through this public IP address and this public address and three public IP address and this port. And by the way, if that didn't work, you can also communicate through turn, because this turn server, this turn server, this turn server, this IP address of the turn server. And also, by the way, just in case, I don't know, because you might want to communicate locally if you live next to me, if you're my phone that's connected to my same Wi-Fi. Here's my private IP address, and by the way, that's a security flaw. Exposing the local IP address in the IP address. Someone named Sammy, I forgot his last name, just literally, I read this article yesterday, use the fact that the browser knows your private IP address to actually infiltrate the network. And we're going to talk about it in another video. But boy, that was amazing. And it tells you, like, we expose all sorts of stuff that we don't, at that time, we don't know how harmful it is. But once you do, oh boy. So he, in a nutshell, he used the application layer gateway extension in the router to essentially, with the knowledge that the private IP address, to expose pretty much all the ports, any port in the in the local machine, and he was able to access it from a malicious server. That was beautiful. Well done, sir. So yeah, it exposes also the local IP address in the SDP, right? And then once we have this beautiful offer, which is basically the SDP, we signal it. We signal the offer somehow to B. That's WhatsApp, right? Just send it through WhatsApp, right? And then B creates the answer after setting A's offer. Ooh. So it takes the offer and then sets it locally. It's local description, local session description. There is concept of local description, local session description, and remote session description. So local description is the local one, that's yours, and the remote description is the remote one. So because you're gonna have two SDPs, right? Every party will have two SDPs. One is local, one is remote. So remember this when we get to the code. So B creates the answer, which is its own SDP. It's just called an answer. And then B signals the answer to A, right? Again, when you create the answer, you gotta wait for all the ICE candidates to trickle before you actually send the SDP. Otherwise, you're gonna have a half-assed SDP. And if you have a half-assed SDP, that's useless, basically, right? And then finally, connection is created. Wowzy. Let's do the demo. All right, let's do the demo, guys. So we're going to have two browsers. It's in my same machine. So sorry about that because I don't have another machine to test again, but it's the same exact code. Doesn't matter. So we have browser A and browser B. We're going to use the dev tools to write this because I want to make it as simple as possible so you can see. And then you take that code, guys, and then you just do it on a large scale. Because once you understand the first principle, nothing can stop you. So A will create an offer, browser A will create an offer, that's the SDP, and set it as a local description. That's my local description. B will get the offer, so we're going to send that string to B, to the browser B, and then we'll set it as a remote description because it's not as, right? It's the remote description. And then B will create an answer, sets it as local description because that's its own SDP, and then we're going to signal the answer back to B. That's the copy the string and paste it. And then A sets the answer as a remote description, and that will establish the channel, right? And we're also going to create a data channel, and we're going to just send chat between each other. That's a simple thing, right? We can do the exact same thing with video, but why? Let's just make it simple, right? There are tons of videos out there that explains how to do medias and stuff. We're caring about the basic fundamentals here. How about we jump into it? All right, guys. So I have opened the dev tools on both sides. This is my local peer A, right? And this is peer B, right? That's what we're going to communicate to. And the first thing we're going to do is we're going to create a local connection equal new. I'm going to zoom in so you can see, called RTC peer connection. That's just exist in your browser, right? And the latest, obviously, I'm assuming you have the latest browser. And just like that, right? We created an RTC peer connection, right? And what I'm going to do here is I am going to create a data channel. So I'm going to have a data channel, right? Equal lc.create data channel. Data channel. That's the channel that we're going to communicate through, right? We'll give it a name. I don't know, channel, anything, right? And once we have the channel, we're going to now just have some metadata associated with this channel. So the most important thing is when we receive a message, I want you to print the following, right? Console.log, just got a message, and then plus e.data. That's how the message looks like. So it's a function, It's an event essentially. And I'm gonna do also on open, because that's an important function as well. And I guess just okay, connection open, because that's a very important thing to see, right? And that's it. That's the most important thing we're gonna know. What else we're gonna do? Once we have this information, we want, guys, remember, we're about to create an offer, but before I create an offer, I want to know every time I get an ICE candidate, I want to reprint the service description protocol, the format SDP. I want to reprint it every time, because until we stopped getting ICE candidate, we cannot really stop printing, because we have no idea when the SDP will actually form and finish, right? So what I'm going to do next is take the local connection dot on ICE candidate. There is a function, and says literally take an information. This is the event, and this function does literally nothing but prints the local description. What is the local description? It's essentially just let's just do a function here. Console.log says new ICE candidate reprinting SDP. Just reprint it, because it's very important to reprint it. How do we print it? It's actually JSON.stringify. And let's close this function. And this function is it's a JSON object. What is the JSON object? It's lc.what we're gonna print the local description. That's the SDP. That's the SDP. That's the local SDP, the one we're gonna create. But this is just a function, and this was gonna be called multiple times until we are done with the ICE candidate. Okay, so that's a very important event, right? We can essentially don't do this event and just wait normally, just like for 10 seconds, 12 seconds, but that's just sounds lame, right? Because we want to see what's happening, right? So the next thing we're gonna do is essentially create the offer. So lc.create offer, that's the SDP, because it doesn't exist, and this is a promise. So beautiful, we deal with the promises all the time. So dot then, right, and then we get an offer O, and what do we do with the offer? We actually set the offer on the local description. So all you have to do is just lc.set local description and set the O, right? The offer is what? Is the SDP, guys, right? And we're gonna set it as my local session description. Beautiful. And then when this is done, we can just do, I don't know, console.log set successfully. Boom, boom. Let's do it, guys. Look at this. Look at this. Look at this. We got two ICE candidates, because this is two, right? Printed twice. And this is looks like this is it. This is my ICE candidate. See, I'm gonna take, this is a JSON object, so I'm gonna copy this guy, and now I'm about to do signaling. So I'm gonna take this, I'm gonna tweet it, I'm gonna send it via WhatsApp, and somehow it reached the other party, which is party B. So I'm gonna create a constant here called offer equal paste. Look at this beautiful. This is the SDP by the way. So SDP, so type is offer, and look at this. Is connect through this UDP port, network cost is this, so generation, ICE option, trickled, all of that stuff. Once we have it, we have an object. What do we do next? We create not the local connection, this is the remote connection, right? So RC equal new RTC peer connection, same thing. Boom. What do we do next? We're gonna do something fancy here. Same thing, right? We still need the same ICE candidate concept, right? And so I'm gonna steal a function from this guy, but I'm gonna change this from LC to RC, right? So and this is also RC. So every time we get a new ICE candidate, I want you to reprint the SDP. That's very, very critical, because we're gonna use it for the answering, right? Nice. What else I'm gonna need? I need actually, guys, to Here's the thing. The data channel that we created here, we're not going to create a new data channel. We're going to actually receive it from the other party, because that's the initiator. This is the receiver. So like a client server. So how do I get the data connection? So const data connection is actually rc.onData channel. When we get a new data channel, we get a new function here. And let's just take a look at this function. We're going to create a brand new function. When we get it, I'm going to save that channel. Where do we save it? rc.data channel. So I'm going to create a new variable here. It's just easier for me to add it as a property of the channel, right? And then equal e.channel. And that's it. So e.channel is the data channel that we received. So the moment we establish the communication, we're going to capture the data channel and we're going to add our own beautiful stuff. So we still need to do rc.dc dot on message, right? So what do we do here? Anything really. Console.log new message from client, and we do e.data. Boom. So that's the function that prints things that when we receive messages from the client. So now rc.dc.onOpen, very important as well. Console.log connection opened. So that's when we just got the connection. All good, right? It's very, very critical stuff. And that's it. Now, what else do we need to do, guys? Now that we have all the pieces, the thing we need to do is we need to send the remote description, right? Set remote description with the what? With the offer. And when this is done, we want you to say, hey, console, once you have that, just tell me that it's done, right? Hey, offer set. It's just that because it's a promise. Boom. We set the offer. So we took the offer, we set the remote description. What's remaining? Two things remaining. We need to set the local description of my remote server, which is rc.set local description. But in order to do that, what do? We create something called an answer. And once you create an answer, you get a beautiful answer here, right? So it's a promise. Once you get it, you do rc.set local description. Let's just clear this up so you guys see. And then zoom in. We set it as A. But that's also a promise. So once this is done, we say, all right, console.log answer created. Boom. All right. So that will set the answer, and that will trickle the ICE candidate. And once we have all the ICE candidate, we got 2. We now have our answer. I'm going to copy this exact puppy, go back to my client, const answer equal this. I'm signaling back now, signaling that SDP back to the client. Boom, we got the answer. What do we do with the answer, guys? We essentially just have one thing remaining, which is local connection dot set remote description answer. And we can decide to wait, or we'll just do that. And let's pray that is done. Look what we have. Connection opened. Connection opened. So we got the connection. We got the data channel. So now if I do dc.send, which is the data channel here, and I'm going to say, yo, pair B, what up? Immediately got it. The on message data channel was received here. I'm gonna copy and paste the code for you guys as well in the description, or maybe I'm gonna push it to GitHub. So we got UP, what up? And now we do what? How do I send message back? Oh, we have it. DC rc.dc. Remember .send. Fine. What about you, fam? And then we got it back. That's the simplest, most elegant WebRTC I can think of, right? You can do the same exact thing with a media or a mic. The only difference that you do is you do lc.add track. That's the only difference. You create a stream from your video from my camera, and you throw that camera stream to the add track, and it works exactly the same, right? So once you copy this code, whether this is on the same machine, because they found the fastest way to communicate through my private IP address, right? Which is I believe one of those, right? I think it's the IPv6. They went through the IPv6 to communicate. So guys, that's it. That's how we do WebRTC. Very simple. Again, you can pause the video and watch me what I did, or just basically copy it from GitHub. I'm gonna push the code as well. Back to the slides and let's complete this video. All right, guys. So the demo was awesome. It was very simple, elegant. That's what I like about things. I like to simplify and break things into its basic, most common components and understand every single line of code. Hopefully you enjoyed that. So how about we jump into the pros and cons? Pros, what is good about WebRTC? Peer-to-peer is great. That's the fastest path, right? I keep saying that, right? Because if I can communicate to you directly, I do not have to go to an actual third party to communicate to you. It's just directly to you. Yeah, obviously it's the internet, so we're passing through all the routers, but all the routers, they don't look at the content if it's encrypted. Some routers with ossified protocols, software, look, and sometimes they block, but no, most of them, they just pass the packets. So peer-to-peer is great. Low latency for high bandwidth content is great. If you have UDP, just shove the UDP, just pipe and just throw all the content. That's beautiful video, right? If you can get a pure peer-to-peer UDP, that's low latency right there, right? And if you're closer and closer to each other, you get the best performance. Standardized API. You saw the API. It's very beautiful, very elegant, right? And then it works right from my browser. I didn't open Visual Studio Code. I didn't install any npm packages and all of that garbage. I don't like to do any of that stuff. I like to work with the basic vanilla stuff. That's just me. All right. Cons. What's bad about this? Well, sometimes peer-to-peer doesn't work, so you need a turn server. But maintaining stun and turn server, if something is outside your jurisdiction, let's say, that's a lot of work. Especially turn. Not much stun, but turn servers, that's a lot of work, guys. It's expensive. Obviously, you're gonna maintain a public IP address. You have to pay for it, and you have to maintain, make sure it's all up and running. Yeah. And yeah, all the traffic goes through that choke point. I don't see a value, to be honest, compared to just do a reverse proxy and have an actual server that you have full vision, right? On, right? This is a centralized server that you control. Just do that, application layer server. I might be wrong there, and I don't know. I have the numbers, but I still believe having more control over some turn server, building your own from scratch is way better. And I believe that what Discord did, they built their own turn servers, right? It's not just relaying packet. They have a little bit more control. They decrypt the traffic. They look at it definitely. I don't, let's say definitely. I say maybe they look at the traffic, because how else they can filter and see the stuff, right? Peer, allegedly, I don't know. Peer-to-peer falls apart in case of multiple participants. Yeah, guys. Yeah, that's what Discord did exactly, right? Because let's assume you have 100 people want to communicate with each other. Would you establish a peer-to-peer connection? That's what, hundreds times 100. That's a lot of connections, right? Because everyone needs to connect to everybody. 99 times 99 times 99 times 99. That's exactly what it is. 99 times 100, right? So that's a lot of connections. It's a mesh, right? But if you have a centralized server, just connect everybody to that centralized server, and you control the traffic. So everybody has one beautiful connection to you, and you as a server has all the connections. So it's just way better, right? Sometimes WebRTC doesn't work for this gaming. You cannot build a game with multiplayer game with WebRTC. I mean, you can if it's 3 players, but I don't see it. I don't see it working with 100 players, to be honest. I might be wrong. More WebRTC stuff. Again, guys, all the resources that I researched during this journey is in the description. So knock yourself out. But let's talk about some of the stuff that I didn't discuss in this channel. Media API, that's I didn't discuss, I didn't show you guys. It's literally called get user media function. You call it and you put it a dev element, and it will show you the camera or the microphone. That gives you a beautiful object stream. You take that stream, you shove it into the RTC connection, and it works exactly like we explained, right? So this is a nice tutorial by HTML Rocks. They explain this very nicely if you want to look at how to do like an actual video chat, right? But what we did is the basic concept. What you send does not matter, right? You can use the data channel to send anything you want, right? But if you want, that's for arbitrary data. But if you want to send media and audio, you use the stream, and a proper stream that uses a different protocol. So on ICE candidate, we saw that right function, that event, right? Every time I got an ICE candidate from the system, that function was called, right? And you can see the ICE candidate, I think e.ice candidate. You can get it. But I don't really care. I just want to reprint the SDP, because the SDP will always get updated every time you get an ICE candidate. Hey, there's a stun server. Hey, there's this. And it's going to take more time if I was actually had a turn and stun server. But I didn't, because I don't need to. I'm communicating locally. But I'm going to show you how to do that as well. So to maintain the connection as new candidate comes, sometimes you need let's say that port that you communicated with peer-to-peer just got destroyed. I don't know, got blocked by the firewall. You want to find a new ICE candidate. How do you communicate it? You already communicated the SDP, right? What if a new candidate comes after the SDP has been sent? That's when you use add ICE candidate, which is pretty neat. I didn't have to, because I'm not building a full-fledged application here, but some example out there actually shows you how to do this, right? And the idea is every time you get an ICE candidate on the client, you take it and you send it to the other party, either with a signaling or via the same exact SDP connection, if it's already alive and well. So on ICE connection tells you candidate tells you there is a new candidate after the SDP has already been created. The candidate is signaled and sent to the other party, and that's it. The SDP party use add candidate to add it to its SDP, right? So you get a brand new SDP. So you can choose to resend that, but I don't think you need to. Once you add an ICE candidate, that's it. It's just it will be up to date, right? So that's another thing I wanted to talk about. Custom and turn stun server. To me, when I created an RTC peer connection, I didn't pass a configuration, but you can essentially decide to pass a configuration, and that configuration looks like this. You can essentially specify ICE servers, and ICE servers is, we know what ICE is now, right? This is my turn server. This is the username, credential, because you cannot just have freebie server, right? You have to have credentials, right? So that's the stun server on Mozilla, for example, and this is the username password, right? Some stun servers are public. We're going to show that, but that's how you create one. If you want to spin up your turn server, we're going to show how to do that. There is an example. There is an open source library that's spinning up your own turn server, and just get that IP address and shove it here. You're done. So you can create your own stun and turn server with this beautiful project called CoTurn. So give them a shout out. CoTurn, GitHub. It's a free open source project to spin up your own stun server. And once you have an IP address for that, you put in the ICE configuration as we showed here. Voila. Right, and then you have a beautiful new ICE candidates. Public stun servers, you can use the Google ones. There's a bunch of public stun servers, stun 1, 2, 3, 4, and there is one stun protocol here that I saw it. I don't know if it's working or not, but this is the one I collected from the internet as well. So yeah, we have a bunch of stun servers you can use publicly if you want to. So for example, if you want this to actually work, you have to add a stun server, and if you want to communicate with two parties that they don't live in the same NAT as I did. Thank you so much, guys. I appreciate you for the patience for this WebRTC, because I made a video WebRTC around 2 months ago explaining how complex this technology is, and I think I'm a little bit closer to the understanding of WebRTC, and that's why I made the video, right? Again, there's so much we can dive deep into the SDP itself or the SIP protocol. There's so much other protocols that communicate, but I hope this video gave you the understanding and necessary understanding to understand WebRTC before you actually use it. Because I always say that don't use the technology without understanding it. It's just me. You can have your own opinion, but I believe anyone who uses the technology, you really need to understand it, because you're an engineer, you have to take pride of your work. All right, subscribe for more backend and other software technology topics. I'm gonna see you in the next one. You guys stay awesome. Goodbye.